In this paper we study meteoroids. And meteoroids are so interesting because they have not been altered for a very long time, since the beginning of the solar system. So resolving individual molecules in a meteoroid gives us insights about the origin of the solar system and the origin of life on Earth. And here now, for the first time, we use a tool that is atomic force microscopy, which we invented here at IBM and developed further to give atomic resolution on a single molecule. And we apply this tool to study molecules of meteoroids. And this tool adds to the existing tools, and we hope that it gives us in the future new clues about the message that these meteoroids can tell us about the origin of the solar system and life on Earth.
One of the core strengths of atomic force microscopy is, first of all, its single molecule sensitivity. So we can really have a look at single molecules from specific samples. And also with AFM, we can really atomically resolve the spatial structure of single molecules. So that is really one means to get real space images with submolecular resolution of single molecules. And that's how we then, in the end, really could have a look at single molecules from a meteoritic source.
We got a sample of the Murchison meteorite from NASA, and this we investigated using our low-temperature AFM.
So we first got the pure meteorite sample, so it was essentially grinded meteorite powder that we then tried to bring onto our sample surface to investigate it. But that was actually pretty challenging because this sample contains also a lot of molecules that we cannot resolve with AFM. And so one step along the process was that it needed to be, well, treated in addition. So we collaborated with chemists from the University of Santiago de Compostela, and they extracted some fraction of this meteorite powder to really extract more molecules that we can actually resolve with our technique. And with that, we increased the number of molecules during one measurement run that we could actually resolve with that technique. So that was one part. And then, of course, we wanted to make sure that the molecules that we found, that they really also stem from this particular meteorite. So we made cross-checks with other more traditional characterization methods. And so for that, we collaborated with people from also from different universities that, well, essentially cross-checked our results and verified that the molecules that we saw really stem from this Murchison meteorite.
What's important for the future is the benefit of AFM is twofold. One is that we have this single molecule sensitivity, so this makes it possible to detect even very trace amounts of molecules that might be missed by other techniques. And the second is that AFM can complement the standard tools as NMR, mass spectrometry, and gas chromatography by having a very good isomer-specific identification of molecules, because we get direct images. And there are a few molecules that can only be resolved if we add AFM as a complementary tool to the existing tools. One important thing is IBM is not to replace any of the tools. It just gives a different angle, mainly through its single molecule sensitivity, so it gives complementary information that can add to the other tools. But for sure it will not replace the other great tools that we have to study meteoroids and molecules in general.
So since we now showed that this method works also for extraterrestrial samples, of course the next step is to really maybe get some other samples from meteoroids that are not that well characterized, so that we can maybe really add some insights into how the structures in other meteoroids look like, so that we can maybe really find new structures that have never been investigated or that have never been found in extraterrestrial samples. That would be pretty cool.